Hi there. Okay, great work trying to upload some of your earthquake experiences. Now, hopefully by now you've seen on the map and can show some different earthquakes that we've experienced here in Bhutan. And so some things to note: intensity, right? Remember, is the measurement of shaking and damage. But while this is valuable to calculate our own experiences, what our map shows us is that intensity really varies from location to location. And a few key points to remember is that intensity is dependent upon the infrastructure and the amount of development in a certain area, how earthquake resistant buildings are actually constructed, the underlying geologic structure, what's going on in the soils, the bedrock in one region. Remember, structure being one of our key components when we think about the geosphere. But finally, the main controlling factor is really the distance from the earthquake event. So that means identifying an earthquake location is really important. And while intensity can give us that quick data in order to respond to earthquakes, it doesn't tell us the whole story. So we have to look into the background information behind earthquakes to really understand in more depth. This animation shows the different types of waves that can be generated by an earthquake. And we're going to break this animation down one by one, because earthquakes ultimately release their energy in many different ways. So when we're talking about intensity, we really are describing the surface waves that earthquakes generate, the ones that travel across the Earth's surface. And these are actually the slowest type of waves that we see. Earthquakes also generate what's known as body waves or seismic waves. And these are waves of energy that travel through the Earth's surface. And there's two types: P, primary waves, and S, as in secondary waves. So just to show you a little bit, we have an earthquake which occurs over here. And then it sends out two waves immediately. You can see this first red wave being the P wave, this second S wave as the secondary wave. Now, the difference between P waves and S waves are essentially how they function. This isn't something you need to remember, but P waves, you can think about them as compressional, pushing a solid in between. And S waves, they're shear waves. They move back and forth. But notice how if each of these stations, each of these locations was a recording station, that these P waves meet before the S waves. We'll watch that one more time, as we can see. Earthquake happens. The P waves are traveling faster than these S waves. You'll see these yellow waves out here, which represent the surface waves. I want you to watch those one more time. As the surface waves go across, they're traveling a lot slower, and they're meeting to the locations at different times. And notice again, the further that the surface waves get, the less shaking that occurs, showing this distribution of intensity. So these P waves and S waves that travel through the surface are really important for us to think about when we're looking at earthquakes. And moving forward, to interpret these P and S waves, we can use devices called seismographs. And these record and measure the shaking that's caused by earthquakes. So these devices have been around for upwards of 100 years. And while they are getting sophisticated, more technological, at the end of the day, they really rely on the same technology, which is just having a weight that's hung independent and a recording device where they can measure shaking and measure the movement and energy. So these seismographs, they can interpret the distance from an earthquake by measuring the time lapse between P and S waves. If the seismograph is close to the earthquake event, then the P waves and the S waves are going to be very close on the record, right? Because those two won't have traveled far. However, if the seismograph is significantly further away from the earthquake location, the P and S waves will have a longer delay. We'll be able to see the difference. And using mathematical calculations, these earthquakes can then tell how far away an earthquake occurred. So a good analogy that you can think of for these P and the S waves is something like lightning and thunder, right? When we think about lightning and thunder, lightning is something, it's a flash in the sky that we see automatically. And then the thunder is the energy that we hear, usually with the delay. And from your experience, you know that the bigger the gap between the flash of lightning and the hearing of thunder, the further away that lightning strike occurred. Just like we talked about in remote sensing, that light is traveling in waves. That sound is traveling in waves. And so it's just two different mechanisms of energy. So it's the same with these P and the S waves. So let's take a look one more time. We can see right at the earthquake center, this red and blue register of the shaking was almost immediate. For these other stations, you can see where the red waves are first registered, and then see the time lapse between the blue waves. One interesting thing to note, all the way at this station over here, we didn't even have any S waves recognized. And that is because these S waves can't travel through liquids. They can only travel through solids. And this is going through Earth's outer core being molten liquid, particularly iron, nickel. So, what you need to remember is just that P and S waves can help stations track how far these earthquakes occur. And so, to bring this into locating earthquakes, we can think about this process, it's called triangulation. Now, say we have a seismograph, and it's able to tell how far away an earthquake occurred. However, that information doesn't tell us exactly where this earthquake occurred. It only tells us how far away from the station. So you can imagine one station records the earthquake distance, and then it can plot a circle around that station to estimate where an earthquake was felt. So for example, in Europe, if there's a station in the Romanian city of Bucharest that recorded an earthquake at a certain distance, you could plot a circle around that, that station in order to interpret where this earthquake might have occurred. But in order to find that location, if we can add data from other stations, say one that was in Ankara and then one that was in down in Sicily, we could try to find the location, the match between all those readings in a certain amount of time. And that match, that triangulation, will allow us to pinpoint where one of these earthquakes happened. That pinpoint is what's known as an epicenter. The epicenter is the location on the Earth's surface where the earthquake starts. This is an important word. So that being said, we can talk about epicenters and locations as being important to understand earthquakes. So here's my next challenge for you. I'm going to show you a new map of Bhutan with earthquake locations from the last 50 years. These were recorded with those seismographs and triangulations. So what I want you to do is look at this map and compare your earthquake experience. Your data will also be plotted on here. And then what I want you to do is ask yourself, what patterns do you notice in earthquake location here in Bhutan? Are these earthquakes random in their locations, or is there any spatial organization? Explore this map and see what you can find out. Okay, good luck.